Hi, Miss Patterson here. Today we're going to go over transport and concentration gradient of a plasma membrane. This is for my biology class. So let's talk about a cell membrane. A cell membrane, remember, is a phospholipid. It's going to have this hydrophilic head and hydrophobic tails. So this area is going to like water. This area is not going to like water. This area over here is going to like water. So the inside of the cell, the outside of the cell is what we call an aqueous environment. So they really enjoy water. This part of the plasma membrane does not. So this is my hydrophobic. This is going to be the one that's not going to want water. Remember, all these tails are a bunch of hydrocarbons, and hydrocarbons are very nonpolar. The hydrophilic heads are very polar, and they like water. So we have a phospholipid bilayer. Bi means two, so I have two layers. I have these proteins that are embedded in this plasma membrane, and this membrane has a very specific function. It likes to regulate. It's going to control what goes in and out of the cell. It's going to be very selective. It's going to support and protect. This is going to give the cell shape. It's going to protect it from dehydration, protect it from material coming in that doesn't need to. So this is going to be a very selective, very supportive, very regulating type of membrane. It's going to be flexible. It's going to allow this animal cell to bend and flex and move. You're going to find a cell membrane in plants, and that can be flexible up against the wall of the cell wall. If it starts to dehydrate, or if I have some type of hypertonic situation happening, this membrane can pull in. So this is going to be very flexible. It's going to be very movable. And we have this type of fluid mosaic model. And if you remember that, we have this area where everything moves. I have these proteins move, these phospholipids move. So this is also makes it very what we call fluid, and that makes it flexible. Proteins within this phospholipid bilayer, they're going to be different types. I have ones that are going to go all the way through. They're going to be what we call a trans protein. It's going to, trans means across, so transatlantic means across the Atlantic. Transmembrane means it goes across the membrane. I can have these as a channel or as a pump. A channel is going to allow material through. A pump can kind of force material through. So these can have different types of functions. I have ones like this. It's going to be a protein. I can have a carbohydrate. I can have some type of lipid. And then this is going to help to recognize and communicate. And I can have ones that are on the peripheral of the cell membrane. This is going to be assisting in chemical reactions that can happen inside the cell. So this would be the inside part of the cell, and this can allow certain activities, certain reactions to happen inside the cell. So here we have that fluid mosaic model I was talking about. All of these pieces can move. So here I have proteins. These are going to be inside, embedded inside this membrane. I'm going to have some that are going to be on the outside. These are going to be peripheral proteins. Ones that are going to be going through are trans proteins. And all of this stuff can move. So if this protein needs to get over here, it can just kind of swim its way through, and all these phospholipids will move and shift, and it will go over here to this way. So it's fluid because it can move. And it's a mosaic because of all of these pieces embedded inside that phospholipid layer. I have permeability. So permeability is the ability of solutes or substance to pass what's called a membrane. These membranes have certain size openings, and they can let in pieces that are really small through. So you see this size right here? I can let the purple circles through, I can let the green ones, I can let the beige ones, but these big red discs, which are red blood cells, these cannot go through. So everything else can pass and we can move stuff back and forth, but these red blood cells are going to be stuck on this side of the plasma membrane. So this can create what's called homeostasis. I'm going to have an equal number or a balance of material back and forth across the membrane as long as it can go through. it's going to be selective. So remember, it's not letting everything through. These red blood cells are staying on this side of the membrane. But my purple, my green, and my beige, these can pass back and forth however they want. This can also control the speed of which material flows through. So we'll talk about gradients here later on, and then that will make a little bit more sense how I can get material to go through fast or slow. You have cytoplasm. This is going to be the solution in the cell that contains many different substances. So outside of the cell is going to have a different concentration than what's on the inside. So my cytoplasm is all of this space. See all this space that's in here? It's holding my Golgi, it's holding my lysosomes, it's ribosomes, mitochondria, all the stuff that's around that. That is my cytoplasm. This whole space here contains everything in it. This is my cytoplasm. The name for what the gel-like substance is your cytosol. So cytoplasm is made up of cytosol, and think of cytosol kind of like a Jell-O fruit salad type of thing. The Jell-O is going to be like the cytosol, and then all the fruit pieces are suspended in it. The whole thing is Jell-O. So like the whole thing is cytoplasm, but the Jell-O surrounding it is kind of like the cytosol. You have a concentration gradient. This is the difference in concentration amounts on either side of a membrane. So when material wants to go through a membrane, it wants to go from an area where it is in a higher concentration to a place where it is in a lower concentration. So right now we're going to say it is these pink spheres. So I have less over here and I have more over here. So I have what we call a high concentration gradient. This does not like being here. It wants to come over here where it's a low concentration gradient. So it is going to diffuse or go across this membrane, and it's going to go over here. People do the same thing. If you're in a really crowded room, people don't want to be all bunched up together. They want to spread out and go to a place where there's less people. Molecules want to do the same thing. So these are going to diffuse, and they're going to go across that membrane from a high concentration to a low concentration. Now, the more I have over here, the less I have over here, the faster this can go. The more this starts to equal out the same number here, I'm going to start slowing down. So the amount of concentration I have over here can drive how fast this diffusion happens. So here we have molecules. Okay, I've got some material here. I have a high concentration, and this high concentration wants to go here. So the matter is going to, these solutes are going to start coming through this membrane, and I'm going to have some here. So it's going to move through fast. Eventually, I'm going to get to the point where I'm going to have the same number of solutes or same number of these little molecules on both sides of the membrane. And when we hit that, we hit what's called equilibrium. And when equilibrium happens, these molecules don't stop moving. They're constantly going back. So if this one moves over here, one of these is going to go over. So they're going to constantly be moving back and forth, but they're going to be still equal on both sides. And we call it, when you have material that passes through a membrane that is not water, we call that dialysis. So diffusion of solutes is from a high to a low concentration. It's a diffusion, and that specific type is going to be called dialysis. So dialysis is the movement of solutes. So when we have passive transport, no energy is needed. It's going again from a high concentration to a low. So here I see I've just got a few green dots, I've got a few brown dots, and I have more over here. This matter wants to go to where it's lower. There are some that can transport and just go diffuse right through this membrane. But I have some that are not able to. They're either going to be polar, they're going to be charged, or they're going to be very large. And if they're large, charged, and polar, they've got to go through a protein that goes across that membrane that allows it to pass through. If I have something that is nonpolar or is very small, or gas, that can go through this membrane without any help. But the other ones, large, charged, and ones that are polar, have to go through some type of membrane, a channel, to be able to get it from one side to the other. And these are very specific. So if this is going to, let's say this is salt, all this protein is going to attract is salt ions. If I need to, or salt molecules, if I need to do some type of water, all it's going to attract is water. Nothing else will get through but that. So these trans proteins, these channels, are very specific. So I have a low concentration, I have a high concentration, and it's going to move from a high to a low concentration. There are some where you need energy. This is when I have to go against my concentration gradient. With passive, we're going with it. I'm going from high to low. It's going to be spontaneous. It's going to happen on its own. But there are times when I need a big concentration of molecules here, and I need to keep adding more. Remember, these don't want to be here. They want to be over here where it's lower. So you have these pumps that are going to be powered with ATP or have some type of electrochemical gradient that is going to pull these in. It's going to force these molecules to go to an area that's high. So we call that going against the concentration gradient, because it is going against what it wants to do. It wants to go this way, but this pump isn't letting it. It's forcing more into an area where it doesn't want to go. So low concentration, high concentration, it's going to pump it in. So if I have to go against it, I need energy to be able to do that. And we're going to do more with active here later. All right, passive, there's different types. So I have diffusion. This is going to be the spreading of molecules from high to low. Remember, I have a high concentration here. These molecules don't want to be here. They want to be spread out. And so this is naturally going to spread out. If you've ever dropped food coloring in water, you'll see it will be real dark in one spot, but then eventually it starts to spread out. It's just spontaneous. It's just naturally going to want to go to a place where there is no food coloring and dye, and then eventually it's going to be spread out evenly throughout that water. Here I have what's called a dialysis bag. Remember, dialysis is when solutes pass back and forth. And so here I have water and I have salt, a salt solution. And on the outside of the bag, I have 5% salt, and inside the bag, I have 20% salt. So I have a little bit of salt out here. I have a lot of salt inside. So what direction would the salt, the solute, the salt want to go? So the salt is going to want to go outside of the bag because I have more salt in here than I do outside. And this is diffusion. So diffusion, we're talking about solutes moving back and forth, not water. We'll talk about that here in a minute. So dialysis bag is going to allow solutes to go back and forth. So here I have another bag. This time I have 5% salt solution. The outside solution is 20% salt solution. So think about it. Where does my salt want to go? Where do I have a higher concentration of salt? It doesn't want to go there. It wants to go to a place where there's less. So what direction is the salt going to want to go? It's going to want to go into the bag. I have less salt here. I have more salt out here. So the salt is naturally going to diffuse into this bag. So diffusion through a membrane, I can have polar molecules can go through. This protein will attract just this specific type of polar molecule. I can have nonpolar gases. This will just diffuse right through that membrane. I don't need any help with that. But remember, anything large, charged, or polar has to go through some type of channel, some type of pump to be able to let it go. It can't go through because these hydrophobic tails don't like to play with those. So low concentration, high concentration. Again, I want to go from a high to a low, and it's going to be spontaneous. So now let's talk about osmosis. So we've been talking about diffusion, And diffusion is talking about solutes. So remember, solutes are the material that's inside the water. So salt water, salt was my solute, water is a solvent. So when we talk about osmosis, we're talking about the solvent of most solutions, which is going to be water. Okay, so water is going to be traveling back and forth. So we got to think about this a little different. I have 5% glucose solution. So if I have 5% glucose solution, I'm going to have 95% water. If I have 20% glucose solution, I'm going to have 80% water inside this bag. So remember, like water wants to go where it's more concentrated to where it's less concentrated. It wants to go down its concentration gradient. So where do I have more water? Do I have more water here or do I have more water here? So the question is going to be, I'm going to be moving from a high concentration to a low concentration. So it's not going to require any energy. And then I just have to think, where am I going to have fewer water molecules? So I have less in the bag, 80%. I have 95 outside. So this is going to want to go into the bag. So the water will go into the bag. Here I have another one. I have 20% glucose outside. I have 5% glucose inside. So again, it's going to go out of the bag. So now, well, why? So ask yourself, where do I have more water? I have more water inside the dialysis bag. I have less water outside. I have 80% water outside. I have 95% water inside. So I have more water inside. It doesn't want to be there. It wants to leave. So water is going to leave the bag. And what I tell my students is water follows where there's more solute. Okay, so here I have a lot of solute. Water is going to flow this direction because this is taking up the space that water could take up. So I have less water molecules in this area because I have so much more glucose. So if you just think, hey, water is going to follow you the solute that's more, that kind of helps you realize that, hey, I'm going to have a lot less water because I have so much more solute taking up that space. So here we have a U-tube. This is a tube that goes in a U shape, and in the center of it you have a semi-permeable membrane. And it's going to allow certain materials through, and it's going to block other materials. So this membrane blocks these purple spheres, and it allows this yellow spheres to come back and forth. You can see that I have very few yellow spheres on this side, but I have a bunch over here. And all inside of this is I have water molecules. The light blue background's my water. So this wants to go from a high concentration to a low concentration. So these little yellow spheres are going to come over and they're going to go through that membrane. These purple ones can't, but they're going to take up space over here. And as they take up space, they're pushing water out of the way. So this is going to come over. And then water is going to want to equal out too. But I have so much stuff over here. I have these big purple spheres. I have these little yellow spheres that I have the exact same amount of water over here as I do over here. My water's at equilibrium. But it looks like I have more because these solutes are taking up space inside my solution. Okay, so you can actually see this and it looks like magic. It will just start to rise because these solutes have unequal amounts of water on both sides, so the water has to balance out. So it pushes up on this side. It's really kind of neat. There are different types of solutions. So you have hypotonic solutions, hypertonic solutions, and isotonic solutions. So when we talk about these, we need to talk about the environment, like what are you putting that cell into? So let's look at isotonic. I'm going to have equal concentrations. Material is going to flow back and forth at the same rate. So let's look at this blood cell. Okay, blood cells, human blood cells want to stay at about a 0.9% salt solution. So this would be a 0.9 salt solution. Outside of the cell would also be 0.9 salt solution. So if it's isotonic, remember when we talk about those water molecules, they're going to pass back and forth. One water molecule comes in, one's going to leave. And it's just going to keep, one leaves, one comes in, and it's just going to keep being a back and forth. My concentration's going to stay the same. Outside, inside, I'm not going to have anything more or less. And this is what animal cells, our cells, your and my cells, like. They like to have an isotonic environment. They want the same concentration outside as they do inside. Plants, on the other hand, don't care for that. They have this strong, real thick cell wall, remember, and they don't have skeletal systems. So these cell walls have to act as a skeletal system. So they want this plasma membrane. You see that thin line right there? That plasma membrane needs to push up against this cell wall to make it stand up really tight and tall. And so this needs to be pumped full of water. When it doesn't have all that water in there, it becomes what we call flaccid, and it's going to be droopy, and the plants are going to droop. When you have hypertonic, we're talking about the environment, okay? And solute concentration is going to be higher outside of the cell. So you just need to look at, okay, where do I have more solute outside of the cell? That's going to make my environment hypertonic. So what happens is, remember, if this cell is 0.9%, and I have a hypertonic solution, this means my solutes out here are going to be a lot higher. So I have a higher concentration of salts out here, so that means I have less water. I have more water inside my cell. Remember, if I have 9% or 0.9% and I have, let's say, 5%, I have so much more salt out here. This water is going to want to leave the cell and go into this 5% solution. And so the cell is going to shrivel up, and then it can do what's called plasmolyze, and it happens with plants. So you can do, plant cells will do the same thing. If I have a 5% salt solution out here and 0.9% inside, I have a higher salt solution outside, so that means I have less water. So this water inside the cell is going to want to rush out and go from an area of high concentration to an area of low concentration. So now let's look at the opposite. So now I have a solute concentration is lower outside of the cell, and water is going to diffuse in. So again, this is 0.9%. Okay, that's what a cell wants to be. But let's say the outside of my cell is 0. Let's say I have no salt in it whatsoever. Let's say this is distilled water. Now all of a sudden, where do I have more solute? Where's all my salts? I have all my salts inside. So that means I have less water inside than I do outside. So now I have a high concentration of water out here. I have a low concentration of water out here. Remember, water wants to go from a high to a low, and it's going to rush inside the cell. And when it does, it's going to stretch that plasma membrane in an animal cell. It's going to stretch it, and it's going to burst. And then that's what we call, it's going to lyse. Okay, you're going to have a lysing, and it's going to burst open, and it's going to kill the cell. But plants, on the other hand, remember, they have that real tough cell wall. All that cellulose is going to make it really tight. This plasma membrane is going to fill up with water, and it's going to want to burst, but it can't because this cell wall is holding everything in, and it becomes what we call turgid pressure. And this actually, when you water a plant, it's going to fill up these vacuoles real big, and then it's going to have a lower concentration of salts outside, a higher inside, so it will pull in water. And now all of a sudden it's going to perk up, and that's when plants will be droopy. You water them, and then they start to perk up, their leaves come out, because now all of these cells are really full of water, and it's pushing against that cell wall. So hypo, I like to think of a hippo. You can also look at this O right here. It's really big, and so that's going to show that it's just about to pop. If you look at hyper, in like an E right here, it's kind of folding in on itself. You can think of it that way too. But hypo, hippo, or you can look at this O and you can think of it, all right, it's about to burst, it's about to break. So here's an example, hypertonic. My solution outside is high, okay, low on the inside. Isotonic, they're the same. Over here, I have high solutes on the inside, low solutes on the outside, so water is going to rush in. Plants love a hypotonic environment. Animal cells love an isotonic environment. Neither of them like a hypertonic environment. And think of it as it's the solution. So the solution is what we're looking at, not the inside of the plant. So it's the environment. Hypertonic environment, we're looking at the solution. Isotonic, hypotonic, look at the solution that the cell is in, okay? All right, so here's a practice. I have 10% glucose. I have 30% glucose. I want you to think about which direction would the sugars go if they could pass through this membrane. They really can't in a dialysis bag, but let's just pretend that they can for right now. If glucose could leave this bag or come into this bag, what direction would it go? So here I have 30% glucose, and here I have 10% glucose. So I have more glucose inside this bag than I do outside. So the glucose would want to try to leave this bag. In a dialysis bag, glucose can't pass it, but we're just going to pretend that it can for this moment, okay? All right, so now let's look at the water. If I was looking at osmosis, what direction is the water going to go? So I have a lot of sugar here. I have a little bit of glucose here. So where do I have more water? I have more water here. I have 90% water here. I have 70% water here. So remember, I want to go from a high concentration to a low. So I have a high concentration, a low concentration, so the water is going to want to go into the bag, okay? All right, so it's going to want to go into the bag. So if it does that, the bag is going to swell and it can lyse and it can burst the bag. All right, so now let's look at this one. I'll give you a second. Think about what directions the sugars would go if they could go through the bag. And osmosis, what is the direction of the water? So this is going to be 40% glucose, 40%. So that means they're going to be the same. So sugar, if it could move through the bag, would move equally back and forth. If I had water, I have 60% water, 60% water, so it's equal on both sides. So it also will move back and forth through this membrane. So water will go through a dialysis bag, and so if one water molecule crosses, another one will come back in. So the concentration inside the bag is equal to the solution in the beaker. So it is going to go both. It's not just going to stay outside and stay inside. They're going to switch back and forth. You're going to have constant movement through this plasma membrane. So the bag would be isotonic. So now let's look at this one. I have 25% glucose. I have 5% glucose. If the glucose could pass through the bag, what direction would it go? I have a higher concentration here. I have a lower concentration here, so glucose would go into the bag. If I'm looking at water, I have 75% water. I have 95% water. So I have more water inside the bag. The water is going to go from a high to a low, so the water is going to want to leave the bag. So my concentration inside is higher than outside, so the water is going to want to leave the bag. And if it does, then the bag is going to shrivel, or plasmolysis. It's going to shrivel and come together as the water leaves. Now, the glucose will stay inside the dialysis bag because it can't leave, but the water can. You have facilitated diffusion. This is a type of passive, again, large, polar, and charged, cannot go through the cell membrane. It needs help. So I have a protein channel. I have a trans protein that's going to go across that membrane. Again, it's very specific to what it allows through. So this will just allow material to pass through, but again, it's very specific. Water, certain types of molecules. You have ones that are like this that will do a conformational change. This molecule is going to come in and it's going to bind with this molecule right here. And remember, if you have a protein and I change the shape of that protein, I change the function. So this is going to come in and it's going to attach and it's going to cause a conformational change. It's going to change the shape of this protein. And then when it changes the shape of this protein, this molecule that was here is going to leave. And then when it leaves, I change my shape, I change my function, it goes back to this. And it will pull back another one, it will attach, it will change its shape, it will allow it to fall out, and then it's going to change back. So it's kind of like a Pac-Man. It's going to open up, allow it in, go in, change, and then it's going to come back, and it's just going to keep doing that as it's allowing this material through the cell. So I have a high concentration, I have a low concentration, so again, it's diffusion, it's spontaneous, it's going to want to go from an area of high to an area of low. No energy is going to be needed. Now, when you have ones like aquaporins, I'm going to have some proteins that are charged, and they're going to attract charged molecules, they're going to attract polar molecules, they're going to attract very specific stuff to go through, so aquaporins only attract water due to a charge. Now, active transport, I'm going to have another video on that one because that's kind of a more in-depth one. But that's going to require a type of energy, and that energy comes in the form of ATP. This is going to want to go against its concentration gradient. So here you can see I have these sodium cations, okay, and the cation is a positively charged ion. So I have these sodium cations. And then I have potassium cations. These are positively charged too. And you can see over here, I have all these sodiums. I need to pump more sodiums to this side of the cell. And so I have to force it. So to force it, I have to use ATP or energy to get that to happen. So the sodium is going to come in, ATP is going to come, and it's going to be enough to cause a conformational change that will change the shape of the protein to force these sodium cations to this side of the plasma membrane. When they're open, these potassium cations are going to come in, the phosphate is going to leave, it's going to do a conformational change back to its original shape, and it's going to force out these potassium cations into an area. So this is forcing it to go against its concentration gradient, not with it. So if I have to go against it, I need some help. Endocytosis, this is going to be large molecules or clumps of food. This is going to require some type of energy. So here I have a food particle, and the food particle is going to be outside. My plasma membrane is going to come up, and I'm going to create kind of like these little pseudopods or fake feet are going to come up, and they're going to kind of engulf this, and then it's going to pinch off. Remember, we talked about plasma membranes are like bubbles, and so this is like a bubble piece, and this bubble will kind of break away from this membrane. The membrane will close off, and then this little bubble with this food is going to go maybe to a lysosome and fuse with it, and the lysosome will start breaking down this food for energy for the cell later, but it's going to bring stuff into the cell. I can bring in liquids, I can bring in other things, same thing, it comes in, it pinches off, and then this little vesicle, it's a phospholipid bilayer. It's a plasma membrane or a cell membrane, and this is going to go wherever it's needed. But this is going into the cell. Endo means in, cyto means cell. Here you have an amoeba. You see these little things right here, these are called pseudopods. And these pseudopods are going to come around and they're going to touch and they're going to fuse, and then it will start to make a vesicle that will start to dissolve and break down the food source that is in there. And if you guys remember, we talked about certain types of organelles. This is a central vacuole. This is going to pull in water and push out water to create a homeostasis of water inside to try to make it as isotonic as possible. It can remove material and bring material in. Exocytosis, this is going to leave the cell. Exo means out. And it's going to come in and it's going to fuse with this membrane. So remember, we talked about bubbles. This bubble is going to come in and it's going to fuse with this membrane to make one big bubble. So if you guys have ever played in the bubble bath, okay, you guys have had bubbles come together and make one big bubble. And that's what these plasma membranes kind of like to do. They're real easy about coming in and fusing. So this will come in and fuse. This now becomes a part of this membrane, and then it opens it up, and then these green pieces will leave the cell and go wherever it needs to go. So it's going to leave the cell, and then it allows hormones and stuff to travel throughout the body. The vesicle will fuse with that membrane and become a part of that membrane. So here you can see, this is the cell membrane, this is the vesicle, and you can see these little hydrophilic heads, hydrophobic tails. This is going to cause a bubble, and then inside I'll have my material. This will come up and fuse with this and now become one big long piece of cell membrane. All right, that's a long one. We're talking about all these different types of way that things can get across a membrane. We'll go more in depth into some other ones like active transport later on. All right, we'll talk to you later. Bye.